What if the answers to some of the universe's greatest secrets are closer than we think? Imagine a reality where the mysteries that have baffled scientists for decades could be unraveled within our lifetime. From the invisible forces shaping galaxies to the strange signals echoing across the cosmos, space is filled with questions that push the boundaries of human knowledge. Today, we're diving into 50 of these mind-bending mysteries, enigmas that could redefine our understanding of the universe and our place within it. These aren't just distant curiosities, they're puzzles that scientists are actively working to solve, and breakthroughs could happen sooner than you think. So, buckle up as we explore the wonders of the cosmos, where every discovery brings us one step closer to unlocking the secrets of the universe. Stay with us, because by the end of this journey, you'll see the night sky in a whole new light. Now turning to the first of our 50 space mysteries, we delve into the enigmatic world of dark matter. Imagine a substance that makes up about 85% of all matter in the universe, yet remains completely invisible to us. This is dark matter, a mysterious force that doesn't emit, absorb, or reflect light, making it impossible to observe directly. But if we can't see it, how do we know it's there? The answer lies in its gravitational effects. Dark matter's presence is revealed through the way it bends light around galaxies and influences the motion of stars within them. Without it, galaxies would fly apart, and the universe as we know it wouldn't exist. So, what exactly is dark matter? Scientists have been grappling with this question for decades. Some theories suggest it could be made up of particles called WIMP, weakly interacting massive particles, that rarely interact with ordinary matter. Others propose it might be composed of actions, hypothetical particles that are incredibly light and difficult to detect. Despite these ideas, no one has yet been able to confirm what dark matter truly is. The search for dark matter is one of the most exciting frontiers in modern science. Experiments like the Large Hadron Collider are smashing particles together at incredible speeds, hoping to create dark matter in the lab. Meanwhile, detectors buried deep underground, such as those in the LUX and Xenon projects, are waiting for the faintest signals of dark matter particles passing through Earth. Even space-based observatories like the Hubble Space Telescope are mapping the distribution of dark matter across the cosmos, providing clues about its nature. The mystery of dark matter isn't just a scientific curiosity, it's a key to understanding the universe itself. Solving it could reveal new laws of physics, reshape our understanding of gravity, and even shed light on the ultimate fate of the cosmos. As we continue to explore this invisible enigma, one thing is certain: the answers are out there waiting to be discovered. And with every experiment, every observation, we're getting closer to uncovering the truth. Now turning to the second of our 50 space mysteries, we shift our focus to dark energy, a force even more mysterious than dark matter. While dark matter holds galaxies together, dark energy is doing something entirely different. It's pushing the universe apart at an ever-increasing speed. This discovery, made in the late 1990s, completely changed our understanding of the cosmos. Scientists had long assumed that the expansion of the universe would slow down over time due to gravity. Instead, they found that it's speeding up, driven by an invisible force we now call dark energy. So, what exactly is dark energy? Unlike dark matter, which exerts a gravitational pull, dark energy seems to work against gravity, acting as a kind of anti-gravity force. It makes up about 68% of the universe's total energy, dwarfing even dark matter. But despite its dominance, we know almost nothing about its true nature. One leading theory suggests that dark energy is a property of space itself, often referred to as the cosmological constant, a concept first proposed by Albert Einstein. Another possibility is that it's a dynamic field known as quintessence, which changes over time and space. The search for answers is ongoing, with some of the most advanced tools in astronomy leading the charge. The Hubble Space Telescope has been instrumental in measuring the rate of the universe's expansion, providing critical data about dark energy's effects. Future missions like the Nancy Grace Roman Space Telescope aim to take this research even further. Scheduled to launch in the mid-2020s, this telescope will map the distribution of galaxies and supernova across vast distances, helping scientists understand how dark energy has influenced the universe's evolution over billions of years. Understanding dark energy isn't just about solving a cosmic puzzle, it's about uncovering the ultimate fate of the universe. If dark energy continues to dominate, the universe could keep expanding forever, leading to a cold, dark future known as the Big Freeze. Alternatively, if dark energy's behavior changes, it could result in a big rip, tearing apart galaxies, stars, and even atoms. The stakes couldn't be higher, and the answers lie hidden in the fabric of space itself. As we peer deeper into the cosmos, we're not just exploring the unknown, we're uncovering the story of everything. Now turning to the third of our 50 space mysteries, we explore one of the most perplexing questions in science, the Fermi Paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everyone?" This paradox highlights the contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it. Given the sheer size of the universe, with its hundreds of billions of galaxies, each containing billions of stars and planets, it seems almost impossible that we are alone. Yet, despite decades of searching, we've found no definitive signs of intelligent life beyond Earth. So, why haven't we made contact? One possible explanation is the Great Filter hypothesis. This theory suggests that there's some kind of barrier, filter, that prevents civilizations from reaching a stage where they can communicate across the stars. This filter could occur at any point in a civilization's development, from the emergence of life itself to the ability to survive technological advancements. If the filter lies in our past, it means we've already overcome it, and the universe might be teeming with life that hasn't yet reached our level. But if the filter lies ahead of us, it could mean that advanced civilizations inevitably destroy themselves before making contact, a sobering thought for humanity's future. Another possibility is that intelligent life is simply too far away, either in space or time. The universe is unimaginably vast, and even if civilizations exist, the distances between them might be too great for communication. Alternatively, they might have existed millions or billions of years ago, long before humans evolved, or they might emerge long after we're gone. The timing of civilizations could be so mismatched that contact becomes nearly impossible. Despite these challenges, the search for extraterrestrial life continues. Programs like SETI, the search for extraterrestrial intelligence, scan the skies for signals that could indicate the presence of advanced civilizations. Meanwhile, missions to exoplanets focus on detecting biosignatures, chemical markers that could suggest the presence of life, such as oxygen or methane in a planet's atmosphere. Recent discoveries of potentially habitable worlds, like those in the TRAPPIST-1 system, have fueled hope that we might one day find evidence of life beyond Earth. The Fermi Paradox reminds us that the universe is full of mysteries, and the search for answers is far from over. Whether we're alone or not, the quest to understand our place in the cosmos continues to drive humanity's curiosity and ambition. As we look to the stars, we're not just searching for alien life, we're searching for a deeper understanding of ourselves and the universe we call home. Now turning to the fourth of our 50 space mysteries, we delve into the enigmatic nature of black holes. These cosmic phenomena, where gravity is so intense that not even light can escape, have long fascinated scientists and the public alike. But what exactly are black holes and how do they form? At their core, black holes are regions of space-time where matter has collapsed under its own gravity, creating a point of infinite density known as a singularity. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape, a point of no return. the formation of black holes is equally fascinating. Most black holes are born from the remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own weight. These stellar black holes, while incredibly dense, are relatively small in size. But there are also supermassive black holes, millions or even billions of times more massive than our Sun, lurking at the centers of galaxies. How these giants form remains a mystery, with theories suggesting they grow by merging with other black holes or by consuming vast amounts of matter over billions of years. One of the most groundbreaking moments in black hole research came in 2019, when scientists unveiled the first ever image of a black hole. Captured by the Event Horizon Telescope, this image revealed the shadow of a supermassive black hole at the center of the galaxy Messier 87, surrounded by a glowing ring of hot gas. This achievement not only confirmed predictions made by Einstein's theory of general relativity, but also opened a new window into understanding these mysterious objects. Another major breakthrough in black hole research has been the detection of gravitational waves, ripples in space-time caused by cataclysmic events like the collision of two black holes. Since the first detection in 2015, gravitational wave observatories like LIGO and Virgo have recorded dozens of these events, providing unprecedented insights into the behavior of black holes. These observations have revealed details about their masses, spins, and even the nature of spacetime itself. Yet, despite these advances, black holes remain shrouded in mystery. What happens inside the event horizon? What lies at the singularity? And could black holes be gateways to other parts of the universe or even other universes entirely? These questions continue to challenge our understanding of physics and the cosmos. As we explore the nature of black holes, we're not just uncovering the secrets of these cosmic giants, we're pushing the boundaries of human knowledge and redefining our place in the universe. Now turning to the fifth of our 50 space mysteries, we explore the origins of the universe itself, the Big Bang. This monumental event, which occurred approximately 13.8 billion years ago, marks the beginning of everything we know: space, time, matter, and energy. But what exactly caused the Big Bang, and what, if anything, existed before it? These questions lie at the heart of one of the greatest mysteries in cosmology. The Big Bang theory suggests that the universe began as an infinitely dense and hot point, often referred to as a singularity. In an instant, this singularity expanded rapidly, setting the stage for the formation of galaxies, stars, and planets. But while the Big Bang explains much of what we observe in the universe today, it leaves some critical questions unanswered. For instance, what triggered this expansion? And what could have existed before the Big Bang, if anything at all? One of the key pieces of evidence supporting the Big Bang theory is the cosmic microwave background radiation, often called the afterglow of the Big Bang. This faint radiation, discovered in 1965, permeates the entire universe and provides a snapshot of the cosmos just 380,000 years after the Big Bang. By studying this radiation, scientists have been able to map the early universe and confirm many predictions of the Big Bang theory. However, the Big Bang theory doesn't explain everything. For example, it doesn't account for why the universe appears so uniform on large scales. To address this, scientists have proposed the theory of cosmic inflation, which suggests that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. This rapid expansion would have smoothed out irregularities, creating the uniform universe we observe today. While inflation is widely accepted, it remains a theory, and scientists are still searching for direct evidence to confirm it. Another lingering question is what, if anything, existed before the Big Bang. Some theories suggest that our universe is just one in a multiverse, with countless other universes existing alongside ours. Others propose that the Big Bang was not the beginning but rather a transition from a previous state of the universe. These ideas push the boundaries of our understanding and challenge us to rethink the very nature of existence. As we continue to probe the mysteries of the Big Bang, we're not just uncovering the origins of the universe, we're also exploring the limits of human knowledge. What caused the Big Bang? What came before it? And what does it mean for the future of the cosmos? These questions remind us that the universe is full of wonders waiting to be discovered, and that the journey to understand it is far from over. Now turning to the sixth of our 50 space mysteries, we delve into the fascinating and mind-bending concept of the multiverse. What if our universe isn't the only one? What if there are countless other universes, each with its own set of physical laws, stars, planets, and perhaps even versions of ourselves? This is the idea behind the multiverse theory, a concept that has sparked both excitement and debate among scientists and philosophers alike. The multiverse theory suggests that our universe is just one of many, possibly infinite, universes that exist simultaneously. These universes could be vastly different from ours, with different constants of nature, different dimensions, or even entirely different forms of matter and energy. But how did this idea come about, and what evidence supports it? One of the key drivers behind the multiverse theory is string theory, a framework that attempts to unify all the fundamental forces of nature. String theory proposes that the universe is made up of tiny, vibrating strings of energy, and it requires the existence of extra dimensions beyond the three we experience. In some versions of string theory, these extra dimensions could give rise to multiple universes, each occupying its own brane or membrane in a higher dimensional space. Quantum mechanics, the science of the very small, also hints at the possibility of parallel universes. According to the many worlds interpretation of quantum mechanics, every time a quantum event occurs, like the decay of an atom or the spin of an electron, the universe splits into multiple branches, each representing a different outcome. In this view, every possible outcome of every event actually happens, but in a separate universe. While this interpretation is controversial, it offers a compelling way to explain the strange behavior of particles at the quantum level. But if the multiverse exists, why can't we see it? The challenge lies in the fact that these other universes, if they exist, are likely beyond our observational reach. They could be separated from us by vast distances, hidden in higher dimensions, or governed by physical laws that make interaction impossible. This makes the multiverse theory incredibly difficult to test or prove. Some scientists argue that the multiverse is more of a philosophical idea than a scientific one, while others believe that future advancements in physics could provide indirect evidence, such as patterns in the cosmic microwave background or anomalies in particle collisions. The multiverse theory pushes the boundaries of our imagination and challenges us to think beyond the confines of our own universe. If true, it would mean that reality is far more vast and complex than we ever imagined. But whether the multiverse is real or not, the questions it raises about the nature of existence, the limits of science, and our place in the cosmos are as profound as they are thrilling. As we continue to explore this mystery, we're reminded that the universe, or perhaps the multiverse, is full of secrets waiting to be uncovered. Now turning to the seventh of our 50 space mysteries, we encounter one of the most perplexing gravitational enigmas in the universe, the Great Attractor. Imagine a force so powerful that it's pulling entire galaxies, including our own Milky Way, toward it at incredible speeds. This mysterious gravitational anomaly lies in the direction of the Centaurus and Hydra constellations, roughly 250 million light-years away. But what exactly is the Great Attractor, and why does it remain one of the most tantalizing mysteries in modern astronomy? The Great Attractor was first discovered in the 1970s when astronomers noticed that galaxies in our local region of the universe were all moving toward a specific point in space. This motion couldn't be explained by the expansion of the universe alone, suggesting the presence of a massive concentration of matter exerting a gravitational pull. But here's the twist. The Great Attractor lies behind the plane of our Milky Way, in a region of space obscured by dense clouds of gas and dust. This makes it incredibly difficult to observe directly, leaving scientists to piece together clues from indirect measurements. So, what could the Great Attractor be? One leading theory suggests it's a massive cluster of galaxies, perhaps even a supercluster containing an enormous amount of dark matter. Dark matter, which doesn't emit light but exerts gravitational force, could explain the intense pull observed. Another possibility is that the Great Attractor is part of an even larger structure, such as the Laniakea supercluster, a vast network of galaxies that includes our own. If this is the case, the Great Attractor might simply be the gravitational center of this colossal cosmic web. Despite these theories, the exact nature of the Great Attractor remains unknown. Its location behind the Milky Way's obscuring dust has made it a challenge to study in detail. However, advancements in technology, such as infrared and radio telescopes, are beginning to pierce through this cosmic veil. Future missions, like the upcoming Nancy Grace Roman Space Telescope, could provide unprecedented views of this region, potentially revealing the true identity of the Great Attractor. The mystery of the Great Attractor not only captivates astronomers but also raises profound questions about the structure and evolution of the universe. What other hidden forces might be shaping the cosmos, and how do these massive structures influence the fate of galaxies, including our own? As we continue to explore this gravitational enigma, we're reminded that the universe is full of surprises, waiting to be uncovered by the curious minds of future generations. Now turning to the 8th of our 50 space mysteries, we dive into the enigmatic world of fast radio bursts, or FRB. These are incredibly powerful bursts of radio waves that last just a few milliseconds, yet they release as much energy as the sun does in an entire day. First discovered in 2007, FRBs have since become one of the most puzzling phenomena in modern astronomy. They come from deep space, often billions of light years away, and their origins remain a mystery. What could possibly produce such intense, fleeting signals across the vastness of the universe? One leading theory suggests that FRBs are linked to neutron stars, the incredibly dense remnants of massive stars that have exploded in supernova. Specifically, magnetars, a type of neutron star with an extremely strong magnetic field, are thought to be prime candidates. These cosmic powerhouses could generate bursts of energy through starquakes or magnetic field interactions, sending shockwaves of radio waves across the cosmos. Another possibility is that FRBs are produced by collisions between neutron stars or between a neutron star and a black hole, events that release enormous amounts of energy in a short time. But not all explanations are so conventional. Some scientists have speculated that FRBs could be evidence of advanced extraterrestrial technology. Imagine a civilization capable of harnessing the energy of an entire star to power interstellar communication or propulsion systems. While this idea is intriguing, it remains highly speculative, and most astronomers lean toward natural explanations. Still, the possibility keeps the door open for some truly mind-bending discoveries. Detecting and studying FRBs is no easy task. These bursts are incredibly brief, lasting only milliseconds, and they appear randomly in the sky. To catch them, astronomers rely on powerful radio telescopes, such as the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, and the Australian Square Kilometre Array Pathfinder, known as ASCAP. These instruments scan the skies continuously, searching for the telltale blips of FRBs. When a burst is detected, scientists work quickly to pinpoint its location and analyze its properties, hoping to uncover clues about its origin. One of the most fascinating aspects of FRBs is that some of them repeat. While most bursts are one-off events, a handful have been observed to flash multiple times from the same location. This repetition has allowed astronomers to study these sources in greater detail, providing valuable insights into their environments and potential causes. For example, one repeating FRB was traced to a small, star-forming galaxy about 500 million light-years away, suggesting that these bursts may be linked to young, active regions of the universe. As our technology and methods improve, the study of FRBs is advancing rapidly. New telescopes, like the upcoming Square Kilometre Array, promise to detect thousands of these bursts, potentially revealing patterns or commonalities that could solve the mystery of their origins. Whether they are the result of cosmic collisions, magnetar activity, or something even more extraordinary, FRBs remind us that the universe is full of surprises, waiting to be uncovered by the curious minds of future generations. Now turning to the 9th of our 50 space mysteries, we explore the intriguing case of the Oumuamua Object, the first known interstellar visitor to our solar system. Discovered in October 2017, Oumuamua immediately captured the attention of astronomers worldwide. Unlike any object observed before, it had a highly unusual shape, resembling a cigar or a pancake, and its trajectory suggested it came from beyond our solar system. This mysterious traveler passed through our cosmic neighborhood at incredible speed, leaving scientists with more questions than answers. One of the most puzzling aspects of Oumuamua was its shape. Most asteroids and comets in our solar system are roughly spherical or irregular, but Oumuamua was elongated, estimated to be up to 10 times longer than it was wide. This unusual form led to speculation about its origins and composition. Some scientists proposed it could be a fragment of a larger object, perhaps shattered by a collision in its home system. Others suggested it might be a shard of a planet or a piece of a disrupted comet, ejected into interstellar space by gravitational interactions. Adding to the mystery was Oumuamua's trajectory. As it passed through the solar system, it exhibited a slight but unexpected acceleration, which could not be explained by gravity alone. This led to a flurry of theories, including the possibility that Oumuamua was outgassing, releasing gas and dust like a comet. However, no such activity was observed, leaving astronomers puzzled. Some even speculated that the acceleration could be due to solar radiation pressure, suggesting Oumuamua might be an extremely thin, lightweight object like a solar sail. Perhaps the most controversial theory about Oumuamua is that it could be an alien spacecraft. The idea gained traction due to its unusual shape and unexplained acceleration, leading some to suggest it might be a probe or artifact from an extraterrestrial civilization. While this theory is fascinating, most scientists remain skeptical, emphasizing the need for natural explanations. After all, extraordinary claims require extraordinary evidence, and so far, no definitive proof of an artificial origin has been found. Despite the debates, Oumuamua has provided valuable insights into the nature of interstellar objects. Its discovery has prompted astronomers to rethink how common such visitors might be and how we can better detect and study them in the future. Upcoming telescopes like the Vera-C Rubin Observatory are expected to identify more interstellar objects, potentially shedding light on their origins and characteristics. As Oumuamua continues its journey out of our solar system, it leaves behind a legacy of curiosity and wonder. Whether it is a natural object or something more extraordinary, this interstellar visitor reminds us that the universe is full of surprises and there is still so much to learn about the cosmos. With each new discovery, we inch closer to unraveling the mysteries that lie beyond our solar system, and perhaps one day we will find the answers we seek. Now turning to the 10th of our 50 space mysteries, we revisit one of the most tantalizing moments in the search for extraterrestrial intelligence, the WOW signal, detected on August 15, 1977, by the Big Ear Radio Telescope at Ohio State University. This mysterious signal lasted for 72 seconds and has never been explained. The astronomer who discovered it, Jerry Amon, circled the data on the printout and wrote "WOW" next to it, giving the signal its iconic name, the WOW signal was remarkable because it matched the expected characteristics of an interstellar transmission. It was narrowband, meaning it was concentrated at a specific frequency, and it appeared to originate from the direction of the constellation Sagittarius. These features made it stand out from the usual background noise of space, sparking excitement and speculation about its potential origin. Could this have been a message from an alien civilization? Despite decades of searching, no repeat signal has ever been detected. This has led to ongoing debates about what the WOW signal truly was. Some scientists argue it could have been a natural phenomenon, such as a comet or a passing satellite, while others believe it remains one of the strongest candidates for evidence of extraterrestrial intelligence. The challenge lies in the fact that the signal was brief and has never been observed again, making it difficult to draw definitive conclusions. The search for a repeat signal continues to this day, with modern telescopes and advanced technology scanning the skies for similar anomalies. Projects like the Search for Extraterrestrial Intelligence, or SETI, have expanded their efforts using powerful instruments to monitor vast regions of the universe. Yet, the WOW signal remains a unique and enigmatic event, reminding us of the challenges of interpreting signals from deep space and the tantalizing possibility that we are not alone. As we move forward in our exploration of the cosmos, the WOW signal serves as a powerful reminder of the mysteries that still await us. Whether it was a fleeting natural event or a deliberate message from another civilization, it continues to inspire curiosity and drive the search for answers. With each new discovery, we come closer to understanding the vast and complex universe we inhabit, and perhaps one day we will uncover the truth behind this extraordinary signal. Now turning to the 11th of our 50 space mysteries, we delve into the puzzling case of the Pioneer anomaly. As the Pioneer 10 and 11 spacecraft journeyed through the solar system, scientists noticed something strange. Both probes were slowing down more than expected. This unexpected deceleration, though tiny, was consistent and defied the predictions of Newtonian physics and Einstein's theory of relativity. It became one of the most intriguing mysteries in space exploration. The Pioneer anomaly was first detected in the 1980s as data from the spacecraft showed they were drifting slightly off course. The deceleration was equivalent to just a fraction of a nanometer per second squared, but over the vast distances these probes traveled, even such a small discrepancy raised big questions. What was causing this mysterious drag? Was it a flaw in our understanding of gravity or something else entirely? One leading theory suggests that thermal radiation from the spacecraft themselves could be responsible. As the probe's radioactive power sources emitted heat, the uneven distribution of this radiation might have created a tiny but measurable force, pushing the spacecraft off their expected trajectories. However, detailed analysis has shown that this explanation doesn't fully account for the observed deceleration, leaving room for other possibilities. Another intriguing idea is that the Pioneer anomaly could hint at new physics beyond our current understanding. Some scientists have proposed that it might be evidence of modifications to gravity on large scales, or even the influence of dark matter. These theories, while speculative, highlight how even the smallest anomalies can challenge our fundamental understanding of the universe. Despite decades of study, the Pioneer anomaly remains unresolved. The spacecraft themselves are now too far away to provide new data, but the mystery continues to inspire research and debate. It serves as a reminder that even in the vastness of space, the smallest details can hold the keys to unlocking profound truth. As we continue to explore the cosmos, anomalies like this remind us that there is still much to learn, and that the universe is full of surprises waiting to be discovered. Now turning to the 12th of our 50 space mysteries, we venture beyond Neptune to explore the enigmatic Kuiper belt. This vast region, home to icy bodies and dwarf planets like Pluto, holds a puzzling secret, it appears to have far less mass than scientists predicted. This discrepancy has sparked a cosmic detective story as researchers try to uncover what's missing and why. The Kuiper belt is thought to be a remnant of the early solar system, a frozen archive of the building blocks that never coalesced into planets. Based on models of how the solar system formed, astronomers expected this region to contain significantly more material than what we've observed. So, where did all the mass go? One leading theory suggests that the gravitational influence of the giant planets, particularly Neptune, may have played a role. As these planets migrated outward during the solar system's early days, their powerful gravity could have scattered much of the Kuiper belt's material, flinging it into the outer reaches of the solar system or even ejecting it entirely. Another possibility is that the missing mass is still out there, hidden in plain sight. Some scientists propose that the Kuiper belt might contain a population of large, undiscovered objects, perhaps even a distant Earth-sized planet. This hypothetical world, often referred to as Planet 9, could have reshaped the orbits of smaller Kuiper belt objects, altering the distribution of mass in ways we're only beginning to understand. While no such planet has been found yet, the search continues with astronomers scanning the skies for clues. There's also the intriguing idea that the Kuiper belt's missing mass might be tied to the mysterious influence of dark matter. While dark matter is typically associated with the larger scale structure of the universe, some researchers have speculated that it could play a role in the dynamics of our own solar system. If true, this would open up entirely new avenues for understanding both the Kuiper belt and the nature of dark matter itself. As we probe deeper into the Kuiper belt, missions like New Horizons, which flew past Pluto in 2015, are providing invaluable data. These observations are helping scientists refine their models and test their theories, bringing us closer to solving the mystery of the missing mass. The Kuiper belt, once thought to be a quiet backwater of the solar system, is proving to be a dynamic and complex region, full of surprises that challenge our understanding of how planetary systems form and evolve. As we continue to explore this distant frontier, we may uncover not just the missing mass, but also new insights into the history and future of our cosmic neighborhood. Now turning to the 13th of our 50 space mysteries, we shift our gaze closer to home, to the moon, a familiar presence in our night sky, yet one whose origins remain shrouded in mystery. How did our moon come to be? The leading theory, known as the giant impact hypothesis, suggests a dramatic and violent beginning. According to this idea, around 4.5 billion years ago, a Mars-sized object, often called Theia, collided with the young Earth. The impact was so colossal that it ejected a massive amount of debris into orbit around our planet. Over time, this debris coalesced to form the moon we know today. But while this theory explains many aspects of the moon's formation, it also raises intriguing questions. For instance, why is the moon's composition so strikingly similar to Earth? If Theia was a separate body, scientists would expect the moon to have a different chemical makeup. Yet, analyses of lunar rocks brought back by the Apollo missions reveal that the moon and Earth share nearly identical isotopic signatures. This has led some researchers to propose alternative versions of the giant impact hypothesis, such as the idea that Theia and Earth were already similar in composition, or that the impact was so energetic that it thoroughly mixed the materials from both bodies. Another puzzle is the moon's lack of volatile elements like water and certain gases, which are abundant on Earth. This suggests that the moon formed under extremely high temperatures, which would have vaporized these lighter materials. But how did this process unfold in such a way that the moon ended up with a composition so close to Earth, yet so distinct in other ways? These unresolved questions continue to challenge scientists and fuel ongoing research. Future lunar missions, such as NASA Artemis program, aim to shed new light on these mysteries by returning humans to the moon and collecting samples from previously unexplored regions like the lunar South Pole. we may uncover clues that refine our understanding of the Moon's formation. Additionally, advanced technologies and instruments will allow scientists to analyze lunar materials with unprecedented precision, potentially revealing new insights into the early solar system. The Moon's origin is not just a scientific curiosity, it's a key piece of the puzzle in understanding how Earth and other rocky planets formed. By unraveling this mystery, we gain a deeper appreciation of our place in the cosmos and the dynamic processes that shaped our world. As we prepare to return to the Moon, we stand on the brink of discoveries that could rewrite the story of our celestial companion, and perhaps even our own. Now turning to the 14th of our 50 space mysteries, we venture to the outer reaches of our solar system, where a tantalizing possibility awaits the existence of a ninth planet. This hypothetical world, often referred to as Planet 9, is believed to orbit far beyond Neptune in the cold, dark fringes of our cosmic neighborhood. But what evidence supports this idea, and why has this elusive planet remained hidden from our telescopes? The story of Planet 9 begins with the peculiar orbits of several distant objects in the Kuiper belt, a region of icy bodies beyond Neptune. These objects, known as trans-Neptunian objects, follow highly elongated and tilted paths that seem to cluster in a way that suggests the gravitational influence of a massive, unseen planet. In 2015, astronomers Konstantin Batygin and Mike Brown proposed that a planet roughly 10 times the mass of Earth could be responsible for these unusual orbital patterns. This hypothetical Planet 9 would orbit the Sun at an average distance of about 600 times farther than Earth, taking between 10,000 and 20,000 years to complete a single orbit. But detecting such a distant object is no easy task. Planet 9, if it exists, would be incredibly faint, reflecting only a tiny fraction of the Sun's light. Its vast distance also means it moves very slowly across the sky, making it difficult to spot even with the most advanced telescopes. Despite these challenges, astronomers are using a variety of techniques to search for this elusive world. Surveys like the Dark Energy Survey and the Subaru Telescope's Hyper-Subprime Cam are scanning the skies for faint, slow-moving objects that could be Planet 9. Additionally, researchers are refining their predictions of its possible location based on the orbits of distant Kuiper belt objects. The discovery of Planet 9 would be a monumental achievement, reshaping our understanding of the solar system's architecture and history. It could explain not only the strange orbits of distant objects, but also provide insights into the formation and evolution of our cosmic neighborhood. Some scientists even speculate that Planet 9 could be a captured rogue planet, originally formed in another star system before being gravitationally snared by the Sun. As the search continues, the mystery of Planet 9 reminds us of how much we still have to learn about our own solar system. Whether this distant world is found in the coming years or remains a tantalizing possibility, its story highlights the enduring allure of exploration and the boundless curiosity that drives us to uncover the secrets of the cosmos. Now turning to the 15th of our 50 space mysteries, we shift our gaze to a star that has baffled astronomers and sparked imaginations worldwide. Tabby star, also known as KSE 8462852. Located roughly 1,400 light-years away in the constellation Cygnus, this star has captured attention due to its bizarre and unpredictable dimming patterns. Unlike most stars which dim in regular, predictable cycles, Tabby's star experiences dramatic and irregular drops in brightness, sometimes by as much as 22%. These unusual fluctuations have led to a flurry of theories, ranging from natural cosmic phenomena to the tantalizing possibility of alien megastructures. One of the most intriguing explanations proposed is the idea of a Dyson sphere, a hypothetical structure built by an advanced extraterrestrial civilization to harness the energy of a star. The irregular dimming patterns could, in theory, be caused by such a megastructure passing in front of the star, blocking its light in unpredictable ways. This idea, while captivating, remains highly speculative and has prompted intense debate within the scientific community. However, more conventional explanations are also being explored. One leading theory suggests that the dimming could be caused by vast clouds of dust and debris orbiting the star. These clouds, possibly remnants of a shattered planet or comet, could intermittently block the star's light as they pass in front of it. Another possibility is that the star itself is undergoing internal changes, such as magnetic activity or stellar pulsations, which could account for the unusual brightness variations. To unravel this mystery, astronomers are closely monitoring Tabby's star using advanced telescopes and instruments. Observations from the Kepler Space Telescope initially brought the star's strange behavior to light, and follow-up studies using ground-based observatories and the Hubble Space Telescope have provided additional data. These efforts aim to determine whether the dimming is caused by natural phenomena or something more extraordinary. The mystery of Tabby's star underscores the importance of continued observation and open-mindedness in science. Whether the answer lies in cosmic dust, stellar activity, or even alien technology, this enigmatic star reminds us that the universe is full of surprises waiting to be uncovered. As we continue to study Tabby's star, we may not only solve this particular mystery, but also gain deeper insights into the complex and dynamic nature of stars and their surroundings. Now turning to the 16th of our 50 space mysteries, we delve into the vast and intricate structure of the universe known as the cosmic web. This colossal network, spanning billions of light years, is made up of galaxies, gas, and dark matter, all interconnected by thin filaments that stretch across the cosmos like the threads of a spider's web. These filaments form the backbone of the universe, guiding the distribution of matter and shaping the large-scale structure we observe today. At the heart of the cosmic web lies dark matter, an invisible substance that makes up about 85% of the universe's total mass. Though it doesn't emit, absorb, or reflect light, dark matter's gravitational influence is immense, pulling galaxies and gas into its web-like structure. The visible galaxies we see are like beads strung along these dark matter filaments, with vast, empty voids separating the denser regions. This intricate arrangement is a testament to the universe's complexity and the role of dark matter in its evolution. To understand the cosmic web, scientists rely on a combination of computer simulations and astronomical observations. Simulations, such as those created using supercomputers, model the behavior of dark matter and ordinary matter over billions of years, revealing how the web forms and evolves. These simulations align remarkably well with observations from powerful telescopes, which map the distribution of galaxies and gas across the universe. Projects like the Sloan Digital Sky Survey have provided detailed three-dimensional maps of the cosmic web, offering a glimpse into its vast and intricate design. One of the most fascinating aspects of the cosmic web is its role in the formation and growth of galaxies. The filaments act as highways, funneling gas and matter into the denser regions where galaxies form and grow. Without this network, the universe as we know it would look vastly different, with galaxies scattered randomly rather than organized into clusters and superclusters. Understanding the cosmic web not only sheds light on the universe's structure, but also helps us piece together the story of how galaxies, including our own Milky Way, came to be. As technology advances, so too does our ability to study the cosmic web. Future telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope promise to provide even more detailed observations, potentially revealing new insights into the web's structure and the role of dark matter. These discoveries could help answer some of the most profound questions in cosmology, such as how the universe evolved from its early, uniform state to the complex, web-like structure we see today. The cosmic web is a reminder of the universe's grandeur and the interconnectedness of all things. As we continue to explore this vast network, we not only deepen our understanding of the cosmos, but also uncover the intricate processes that have shaped it over billions of years. The journey to unravel the mysteries of the cosmic web is far from over, and each new discovery brings us closer to understanding the true nature of the universe. Now turning to the 17th of our 50 space mysteries, we encounter a puzzling question. Where is all the ordinary matter in the universe? This mystery, known as the missing baryon problem, revolves around the fact that a significant portion of the universe's baryonic matter, the protons and neutrons that make up stars, planets, and everything we see, remains unaccounted for. While we know that dark matter and dark energy dominate the cosmos, the missing baryons represent a gap in our understanding of the universe's visible components. According to our best estimates, only about half of the expected baryonic matter has been detected. The rest seems to have vanished, leaving scientists to wonder where it could be hiding. One leading theory suggests that this missing matter exists in the form of the warm, hot intergalactic medium, or WIM. This elusive substance is thought to be a diffuse, hot gas that fills the spaces between galaxies, too faint and spread out to be easily observed. The WIM is believed to consist of ionized gas, heated to temperatures of hundreds of thousands of degrees, making it incredibly difficult to detect with traditional telescopes. To locate this missing matter, astronomers have turned to innovative techniques and advanced instruments. One method involves studying the absorption of light from distant quasars as it passes through the WIM. By analyzing the faint signatures left in the quasar's light, scientists can infer the presence and properties of this hot gas. Another approach uses X-ray telescopes to search for the faint glow emitted by the WIM, though this requires incredibly sensitive instruments capable of detecting such subtle signals. The search for the missing baryons is not just an academic exercise, it's crucial for understanding the universe's overall composition and evolution. Baryonic matter plays a key role in the formation of galaxies, stars, and planets, and its distribution affects the large-scale structure of the cosmos. By solving the missing baryon problem, we can gain a more complete picture of how the universe works and how it has evolved over billions of years. Future missions and telescopes, such as the European Space Agency's Athena X-ray Observatory, are expected to provide new insights into this mystery. These instruments will offer unprecedented sensitivity, allowing scientists to map the WIM in greater detail and potentially uncover the missing baryons. As we continue to refine our techniques and expand our observational capabilities, the answers to this cosmic puzzle may finally come into focus. The missing baryon problem reminds us that even the most fundamental aspects of the universe can hold surprises. As we piece together the story of where this matter has gone, we not only fill in a critical gap in our knowledge, but also deepen our appreciation for the complexity and wonder of the cosmos. The journey to solve this mystery is far from over, and each new discovery brings us closer to understanding the true nature of the universe. Now turning to the 18th of our 50 space mysteries, we delve into a question that has puzzled astronomers for decades. How old is the universe? At first glance, this might seem like a straightforward question, but the answer is anything but simple. The age of the universe is one of the most fundamental measurements in cosmology, yet different methods of calculating it have led to conflicting results, creating a tension that remains unresolved. One of the primary methods for determining the universe's age relies on the Hubble constant, a value that describes how fast the universe is expanding. By measuring the rate of expansion and working backward, scientists can estimate how long it has been since the Big Bang. However, this approach has produced varying results depending on the techniques used. For example, observations of nearby galaxies and supernovas suggest a faster expansion rate, implying a younger universe, while measurements of the cosmic microwave background, the faint afterglow of the Big Bang point to a slower expansion rate and an older universe. This discrepancy, often referred to as the Hubble tension, has sparked intense debate among scientists. The cosmic microwave background, observed by missions like the Planck satellite, provides a snapshot of the universe when it was just 380,000 years old. These observations suggest the universe is approximately 13.8 billion years old. On the other hand, measurements using Cepheid variable stars and Type 1, a supernova in the local universe, indicate a younger age, closer to 12.5 billion years. So, why does this tension exist? One possibility is that there are systematic errors in our measurements, such as inaccuracies in the distances to nearby galaxies or the brightness of supernova. Another intriguing explanation is that our understanding of the universe's physics might be incomplete. For instance, the presence of unknown forms of dark energy or dark matter could be influencing the expansion rate in ways we don't yet fully understand. Some scientists have even proposed that the Hubble constant might not be constant at all, but could vary over time or across different regions of the universe. Resolving this mystery is crucial because the age of the universe is deeply tied to its composition, evolution, and ultimate fate. If the Hubble tension persists, it could signal the need for new physics, potentially reshaping our understanding of the cosmos. Future missions such as the James Webb Space Telescope and the Nancy Grace Roman Space Telescope aim to refine these measurements and shed light on this discrepancy. By combining data from multiple sources and improving our observational techniques, we may finally uncover the true age of the universe. The age of the universe is more than just a number, it's a window into the history and workings of the cosmos. As we continue to explore this mystery, we are reminded that even the most fundamental questions in science can lead to profound discoveries. The journey to solve this tension is far from over, and each new observation brings us closer to understanding the true story of our universe. Now turning to the 19th of our 50 space mysteries, we explore a question that has captivated both scientists and dreamers alike. How will the universe end? While the age of the universe remains a topic of debate, its ultimate fate is equally shrouded in mystery. The end of the universe isn't just a dramatic concept, it's a scientific puzzle that hinges on the behavior of dark energy, the expansion of the cosmos, and the fundamental laws of physics. One of the leading theories is the Big Freeze, also known as the heat death of the universe. In this scenario, the universe continues to expand at an accelerating rate, driven by dark energy. Over trillions of years, galaxies will drift farther apart, stars will burn out, and the cosmos will grow colder and darker. Eventually, all that will remain is a vast, empty expanse with temperatures approaching absolute zero. This chilling outcome suggests a universe that fades into silence, its energy spread so thin that no new stars or galaxies can form. Another possibility is the Big Crunch, a dramatic reversal of the Big Bang. If dark energy weakens over time or gravity eventually overcomes the expansion, the universe could begin to collapse in on itself. Galaxies would merge, temperatures would rise, and the cosmos would shrink back into an infinitely dense point, a singularity. This scenario raises the tantalizing question of whether the universe could cycle through endless expansions and contractions, a concept known as the Big Bounce. Then there's the Big Rip, a more violent end to the universe. If dark energy grows stronger over time, it could tear apart galaxies, stars, planets, and even atoms themselves. In this scenario, the fabric of space-time would be ripped apart, leaving behind a chaotic, fragmented cosmos. The Big Rip is a stark reminder of the immense power of dark energy and its potential to reshape the universe in ways we can barely imagine. The fate of the universe is deeply tied to the nature of dark energy, a mysterious force that makes up about 70% of the cosmos. Yet, despite its dominance, we know very little about what dark energy truly is or how it behaves. Is it constant or does it change over time? The answer to this question could determine whether the universe ends in a freeze, a crunch, or a rip. Understanding the end of the universe isn't just about predicting its final moments, it's about unraveling the fundamental forces that govern everything we see. As we continue to study dark energy and the expansion of the cosmos, we inch closer to answering one of the most profound questions in science: what lies at the end of time? The journey to uncover the universe's ultimate fate is far from over, and each new discovery brings us closer to understanding the grand story of existence. Now turning to the 20th of our 50 space mysteries, we delve into the enigmatic world of neutron stars. These cosmic remnants are born from the explosive deaths of massive stars, collapsing into objects so dense that a single teaspoon of their material would weigh billions of tons on Earth. Neutron stars are not just dense, they are also home to some of the most extreme conditions in the universe, from their incredibly strong magnetic fields to their mind-bending gravitational forces. One of the most fascinating aspects of neutron stars is their role as pulsars. When a neutron star spins rapidly, it emits beams of radiation from its magnetic poles. If these beams sweep across Earth, we detect them as regular pulses of light or radio waves, earning these objects the name pulsars. These cosmic lighthouses provide scientists with a unique way to study the properties of neutron stars, from their rotation rates to their magnetic fields. Pulsars have even been used to test Einstein's theory of general relativity, as their precise timing can reveal the effects of space-time warping around them. Then there are magnetars, a special class of neutron stars with magnetic fields trillions of times stronger than Earth's. These magnetic fields are so intense that they can distort the structure of atoms and even crack the star's crust, releasing bursts of energy known as starquakes. Magnetars are thought to be behind some of the most powerful explosions in the universe, including gamma-ray bursts and fast radio bursts. Studying these extreme objects could help us understand the limits of magnetic fields and the behavior of matter under conditions we can never replicate on Earth. But the mysteries of neutron stars go even deeper. Their interiors are thought to contain exotic states of matter, such as superfluids or even quark-gluon plasma, which could challenge our understanding of physics. By observing neutron stars, scientists hope to uncover new insights into the fundamental forces that govern the universe. For example, the detection of gravitational waves from colliding neutron stars has already provided groundbreaking information about the nature of space-time and the origins of heavy elements like gold and platinum. Neutron stars are not just cosmic oddities, they are laboratories for testing the laws of physics in ways that no Earth-based experiment ever could. As we continue to study these dense magnetic powerhouses, we may unlock secrets about the universe that have remained hidden for billions of years. The journey to understand neutron stars is far from over, and each discovery brings us closer to unraveling the mysteries of the cosmos. Now turning to the 21st of our 50 space mysteries, we explore one of the Sun's most baffling secrets, the scorching heat of its outer atmosphere known as the corona. While the Sun's surface, or photosphere, reaches temperatures of around 5,500 degrees Celsius, the corona soars to millions of degrees. This counterintuitive phenomenon, where the outer layer is far hotter than the surface beneath it, has puzzled scientists for decades. One leading theory to explain this mystery involves magnetic reconnection. The Sun's surface is a turbulent sea of magnetic fields, constantly twisting and tangling. When these fields snap and reconnect, they release enormous amounts of energy in the form of heat and solar flares. This process could be heating the corona to its extreme temperatures. However, the exact mechanisms behind this energy transfer remain unclear, and scientists are still working to piece together the full picture. Another possibility is the role of plasma waves. The Sun's atmosphere is filled with charged particles or plasma, which can carry energy in the form of waves. These waves might travel outward from the sun's surface, depositing their energy into the corona and heating it up. But how and why this happens on such a massive scale is still a subject of intense research. Upcoming solar missions like the European Space Agency's Solar Orbiter and NASA's Parker Solar Probe are poised to shed light on this mystery. These spacecraft are designed to get closer to the sun than ever before, collecting data on its magnetic fields, plasma waves, and energy flows. By studying the sun's atmosphere in unprecedented detail, these missions could finally reveal the processes that make the corona so incredibly hot. Understanding the solar corona isn't just an academic exercise, it has real-world implications. The corona is the source of the solar wind, a stream of charged particles that flows outward into the solar system. When this wind interacts with Earth's magnetic field, it can create stunning auroras, but it can also disrupt satellites, power grids, and communication systems. By solving the mystery of the corona's heat, we could improve our ability to predict and mitigate the effects of space weather. The sun's corona is a reminder of how much we still have to learn about our nearest star. As we continue to probe its secrets, we may uncover not only the answers to this long-standing mystery, but also new insights into the fundamental processes that shape stars and their environments. The journey to understand the sun's corona is heating up, and the discoveries ahead promise to be nothing short of illuminating. Now turning to the 22nd of our 50 space mysteries, we delve into the intriguing detection of methane on Mars and what it could mean for the possibility of life on the red planet. Methane, a gas often associated with biological processes on Earth, has been detected in Mars' atmosphere in small but significant amounts. This discovery has sparked excitement and debate among scientists, as methane could be a potential indicator of past or even present microbial life. However, the story isn't so straightforward. Methane can also be produced through geological processes, such as the interaction of water with certain types of rock or volcanic activity. This makes it challenging to determine whether the methane on Mars has a biological or geological origin. Scientists are working hard to distinguish between these possibilities, using data from rovers like Curiosity and orbiters like the European Space Agency's Trace Gas Orbiter. These missions have detected seasonal variations in methane levels, adding another layer of complexity to the mystery. One of the key challenges is the short lifespan of methane in the Martian atmosphere. Ultraviolet light from the sun breaks it down relatively quickly, meaning any methane detected must have been released recently. This raises questions about what ongoing processes could be producing it. Is it the result of ancient microbes buried beneath the surface, or is it being released by geological activity? The answer could have profound implications for our understanding of Mars and its potential to support life. Future missions to Mars, such as NASA's Mars Sample Return Campaign and the European Space Agency's ExoMars rover, aim to tackle this mystery head-on. These missions will carry advanced instruments designed to analyze the chemical composition of Martian soil and rocks, searching for clues about the origin of methane. By studying the gas in greater detail and potentially identifying its source, we could take a giant leap toward answering one of the most compelling questions in planetary science. Is there or was there ever life on Mars? The search for Martian methane is more than just a scientific pursuit. It's a quest to understand our place in the universe. If methane on Mars is linked to life, it would suggest that life is not unique to Earth and could exist elsewhere in the cosmos. On the other hand, if it's purely geological, it would still reveal fascinating details about Mars' history and its potential to support future human exploration. Either way, solving this mystery will bring us closer to unlocking the secrets of the Red Planet and the broader question of life beyond Earth. Now turning to the 23rd of our 50 space mysteries, we explore the puzzling phenomenon of the ice giants Uranus and Neptune emitting more heat than they receive from the Sun. Unlike Earth, which primarily gets its warmth from solar radiation, these distant planets seem to have an internal heat source that defies simple explanation. This mystery has intrigued scientists for decades as it challenges our understanding of planetary formation and the behavior of materials under extreme conditions. One leading theory suggests that the excess heat is a remnant of the planet's formation. When Uranus and Neptune were born, the gravitational collapse of gas and dust would have generated immense heat. Over billions of years, this heat has been slowly radiating into space, but not all of it has dissipated. This leftover heat could explain why these planets are warmer than expected. However, this doesn't fully account for the significant difference between the heat they emit and the heat they receive from the Sun. Another possibility involves the internal dynamics of these planets. Both Uranus and Neptune are thought to have layered interiors with icy mantles surrounding rocky cores. The movement of materials within these layers, driven by convection or other processes, could generate additional heat. Some scientists speculate that exotic materials such as supersonic water or metallic hydrogen might exist in their cores, contributing to this internal heat production. These materials behave differently under the extreme pressures and temperatures found deep within ice giants, potentially releasing energy as they shift and flow. The tilted magnetic fields of Uranus and Neptune add another layer of complexity. Unlike most planets whose magnetic fields align roughly with their rotational axes, these ice giants have magnetic fields that are significantly offset. This unusual configuration suggests that their internal structures and heat distribution are far from ordinary. Understanding how these magnetic fields are generated could provide clues about the sources of their internal heat. Future missions to Uranus and Neptune, though challenging due to their immense distance, could revolutionize our understanding of these enigmatic worlds. Probes equipped with advanced instruments could measure their heat emissions more precisely, map their magnetic fields in detail, and even sample their atmospheres for clues about their internal composition. Solving the mystery of the ice giants' internal heat would not only shed light on these distant planets, but also deepen our knowledge of planetary systems across the universe. As we continue to unravel the secrets of Uranus and Neptune, we are reminded of how much there is still to learn about the cosmos. These ice giants, with their hidden heat and exotic interiors, stand as testaments to the complexity and wonder of the universe. Each discovery brings us closer to understanding the forces that shape not only our solar system, but also the countless others waiting to be explored. Now turning to the 24th of our 50 space mysteries, we revisit one of the most dramatic and puzzling events in modern history, the Tunguska event. On June 30th, 1908, a massive explosion rocked the remote forests of Siberia, flattening an estimated 80 million trees over an area of more than 2,000 square kilometers. The blast was so powerful that it was heard hundreds of kilometers away, and shockwaves were detected as far as Europe and Asia. Yet, despite its immense force, no crater was ever found, leaving scientists baffled for over a century. The leading theory suggests that the Tunguska event was caused by the airburst of a comet or asteroid. As the object entered Earth's atmosphere, it heated up rapidly, disintegrating and releasing an enormous amount of energy before it could hit the ground. This would explain the widespread destruction and the absence of a crater. However, the exact nature of the object remains uncertain. Some researchers believe it was a stony asteroid, while others argue it could have been a comet made of ice and dust, which would have vaporized completely upon entering the atmosphere. Another intriguing aspect of the Tunguska event is the lack of physical evidence. No fragments of the object have ever been conclusively identified, despite numerous expeditions to the site. This has led to alternative theories, such as the possibility of a small black hole passing through Earth, or even the explosion of a natural gas pocket beneath the surface. While these ideas are less widely accepted, they highlight the enduring mystery of what truly happened that day. The Tunguska event also serves as a stark reminder of the potential dangers posed by near-Earth objects. If a similar explosion were to occur over a populated area today, the consequences would be catastrophic. This has spurred efforts to detect and track asteroids and comets that could pose a threat to Earth, as well as research into ways to deflect or mitigate such hazards. Despite the advances in our understanding of space and planetary science, the Tunguska event remains an unsolved mystery. It challenges us to consider the unpredictable nature of our universe and the forces that shape it. As we continue to study this enigmatic event, we are reminded of the importance of vigilance and curiosity in unraveling the secrets of the cosmos. With each new discovery, we move closer to understanding not only what happened over Siberia in 1908, but also how we can protect our planet from similar events in the future. Now turning to the 25th of our 50 space mysteries, we delve into the enigmatic source of high-energy gamma rays emanating from the center of our Milky Way galaxy. This region, known as the Galactic Center, is a hotbed of cosmic activity, and the intense gamma ray emissions detected there have puzzled scientists for decades. These gamma rays are some of the most energetic forms of light in the universe, and their origin remains one of the most intriguing questions in modern astrophysics. One leading theory suggests that these gamma rays could be produced by the annihilation of dark matter particles. Dark matter, which makes up about 85% of the universe's mass, is invisible and does not interact with light, making it incredibly difficult to detect directly. However, if dark matter particles collide and annihilate each other, they could produce gamma rays as a byproduct. The galactic center, with its dense concentration of dark matter, would be an ideal place to observe such phenomena. Yet, despite extensive research, no definitive evidence has been found to confirm this theory, leaving it as a tantalizing possibility. Another explanation points to pulsars, rapidly rotating neutron stars that emit beams of radiation, including gamma rays. The galactic center is home to a large population of these exotic objects, and their combined emissions could account for the observed gamma ray signal. However, distinguishing the gamma rays produced by pulsars from those potentially caused by dark matter annihilation is a significant challenge. The overlapping signals and the sheer complexity of the galactic center's environment make it difficult to pinpoint the exact source. Adding to the mystery is the presence of a supermassive black hole at the heart of the Milky Way, known as Sagittarius, a star. While this black hole itself does not emit gamma rays, the intense gravitational forces and high-energy processes occurring in its vicinity could contribute to the gamma ray emissions. Jets of particles, shock waves from supernova, and interactions with surrounding gas and dust are all potential factors that complicate the search for a single, definitive explanation. The study of the galactic center's gamma rays is further complicated by the limitations of our current technology. Gamma rays are absorbed by Earth's atmosphere, so observations must be made using space-based telescopes like the Fermi Gamma Ray Space Telescope. While these instruments have provided invaluable data, they are still limited in their ability to resolve fine details in such a crowded and dynamic region of space. As we continue to explore this cosmic puzzle, the mystery of the galactic center's gamma rays reminds us of the vast complexity of our universe. Whether the source is dark matter, pulsars, or some other yet-to-be-discovered phenomenon, solving this mystery could provide profound insights into the nature of matter, energy, and the forces that govern our galaxy. With each new observation and technological advancement, we move closer to unraveling the secrets of the galactic center and the high-energy processes that shape it. Now turning to the 26th of our 50 space mysteries, we explore a puzzling discrepancy that has left scientists scratching their heads: the Hubble tension. This mystery revolves around conflicting measurements of the universe's expansion rate, a fundamental parameter in cosmology known as the Hubble constant. For decades, astronomers have used two primary methods to calculate this rate: but the results don't align, creating a tension that could reshape our understanding of the cosmos. The first method relies on observations of the cosmic microwave background, the faint afterglow of the Big Bang. By studying this ancient light, scientists can infer the universe's expansion rate shortly after its birth and extrapolate it to the present day. The second method involves measuring the distances to nearby galaxies using objects like Cepheid variable stars and Type Ia supernova, which serve as cosmic yardsticks. These measurements provide a more direct estimate of the current expansion rate. The problem: the two methods give different answers, and the gap between them is too large to be explained by measurement errors alone. This discrepancy, known as the Hubble tension, has profound implications for cosmology. If the measurements are accurate, it suggests that our current understanding of the universe's composition and evolution might be incomplete. One possibility is that there's an unknown ingredient in the cosmic recipe, perhaps a new form of dark energy or an exotic particle that's influencing the expansion rate in ways we don't yet understand. Alternatively, it could mean that our models of the early universe, based on the cosmic microwave background, need to be revised. The Hubble tension has sparked a flurry of research and debate within the scientific community. Some researchers are exploring whether systematic errors in the measurements could be to blame, while others are investigating whether new physics beyond the standard model of cosmology might be required to resolve the discrepancy. For example, theories involving modifications to Einstein's theory of gravity or the behavior of dark energy are being tested as potential solutions. As we continue to refine our measurements and develop new observational techniques, the Hubble tension remains one of the most pressing challenges in modern astrophysics. Resolving it could not only shed light on the universe's expansion, but also deepen our understanding of the fundamental forces and particles that govern the cosmos. Whether the answer lies in tweaking our existing models or discovering entirely new physics, this mystery reminds us that the universe still holds many secrets waiting to be uncovered. Now turning to the 27th of our 50 space mysteries, we delve into the fascinating concept of wormholes, theoretical tunnels through space-time that could act as shortcuts across vast cosmic distances. Imagine folding a piece of paper so that two distant points touch. A wormhole would be like punching a hole through that fold, creating a direct path between them. While this idea has long been a staple of science fiction, it's also grounded in the equations of Einstein's theory of general relativity, which suggests that such structures could exist under the right conditions. However, proving the existence of wormholes is no easy task. For one, they would require exotic matter with negative energy density to remain stable, something we've never observed in nature. Even if they do exist, wormholes would likely be incredibly small, unstable, and short-lived, making them nearly impossible to detect with current technology. Despite these challenges, scientists continue to explore the possibility, using advanced mathematics and quantum mechanics to better understand how such phenomena might work. Quantum mechanics, in particular, plays a key role in this exploration. At the smallest scales, particles can behave in ways that defy classical physics, and some theories suggest that quantum effects could stabilize a wormhole or even allow for the creation of microscopic versions. While these ideas remain speculative, they open the door to intriguing possibilities, such as time travel or instantaneous communication across the universe. The study of wormholes also intersects with other cutting-edge areas of physics, including string theory and the search for a unified theory of everything. By investigating these theoretical constructs, scientists hope to uncover deeper truths about the nature of space-time and the fundamental laws that govern our universe. While wormholes remain a mystery for now, their potential to revolutionize our understanding of reality keeps them at the forefront of scientific inquiry. As we continue to push the boundaries of knowledge, who knows what secrets these cosmic shortcuts might reveal? Now turning to the 28th of our 50 space mysteries, we explore the enigmatic origins of ultra-high-energy cosmic rays. These high-energy particles, traveling at nearly the speed of light, bombard Earth from all directions, yet their sources remain one of the most perplexing puzzles in astrophysics. Cosmic rays are not actual rays of light, but rather charged particles, mostly protons, that carry immense amounts of energy, sometimes millions of times more than what we can produce in the most powerful particle accelerators on Earth. So, where do these cosmic rays come from? One leading theory points to supernova, the explosive deaths of massive stars. When a star explodes, it sends shock waves through space, accelerating particles to incredible speeds. These particles could then become the cosmic rays we detect. However, while supernova can explain some lower energy cosmic rays, they struggle to account for the ultra-high energy ones that defy our current understanding of physics. Another possibility involves black holes, particularly the supermassive ones at the centers of galaxies. As matter spirals into these black holes, it heats up and emits powerful jets of particles and radiation. These jets could potentially accelerate particles to the extreme energies observed in cosmic rays. Similarly, other extreme cosmic events, such as gamma-ray bursts or collisions between neutron stars, might also serve as cosmic ray factories. Yet, despite these compelling theories, pinpointing the exact sources has proven incredibly challenging. One of the biggest obstacles is that cosmic rays are deflected by magnetic fields as they travel through space, making it nearly impossible to trace their paths back to their origins. To overcome this, scientists rely on indirect methods, such as studying the gamma rays and neutrinos that are produced when cosmic rays interact with other matter. These secondary particles can provide clues about the cosmic rays' origins, but the process is complex and requires advanced observatories like the Pierre-Auger Observatory and the Ice Cube Neutrino Observatory. The mystery of cosmic rays also ties into broader questions about the universe's most extreme environments and the fundamental laws of physics. By studying these particles, scientists hope to uncover new insights into the behavior of matter and energy under conditions far beyond anything we can recreate on Earth. While the origins of ultra-high-energy cosmic rays remain elusive, ongoing research and technological advancements bring us closer to solving this cosmic puzzle. As we continue to explore the universe's most energetic phenomena, who knows what groundbreaking discoveries await? Now turning to the 29th of our 50 space mysteries, we delve into the incredible journey of the Voyager 1 and 2 spacecraft, humanity's farthest-reaching emissaries into the cosmos. Launched in 1977, these twin probes were initially designed to study the outer planets of our solar system, but their mission has since expanded far beyond their original scope. After completing their grand tour of Jupiter, Saturn, Uranus, and Neptune, the Voyagers continued their voyage, venturing into the uncharted territory of interstellar space, the vast expanse between stars. Voyager 1 made history in 2012 when it became the first human-made object to cross the heliopause, the boundary where the sun's influence wanes and interstellar space begins. Voyager 2 followed suit in 2018, providing a second data point that has revolutionized our understanding of this cosmic frontier. Out here, the Voyagers are no longer shielded by the sun's magnetic field, exposing them to the full intensity of cosmic rays and interstellar particles. Yet, despite the harsh conditions, these resilient probes continue to send back invaluable data. So, what might the Voyagers encounter as they drift deeper into interstellar space? One possibility is the interstellar medium, a sparse mix of gas, dust, and charged particles that fills the void between stars. By studying this medium, scientists hope to learn more about the composition and dynamics of our galactic neighborhood. The Voyagers have already detected unexpected changes in the density of this medium, hinting at complex interactions between the solar wind and interstellar space. Another intriguing question is whether the Voyagers might encounter any interstellar objects, like the mysterious Oumuamua or Borisov, which passed through our solar system in recent years. While the chances are slim, such an encounter could provide unprecedented insights into the nature of objects born in other star systems. Even without such a discovery, the Voyager's instruments continue to measure magnetic fields, cosmic rays, and plasma waves, offering a unique window into the conditions of interstellar space. The data from the Voyagers is also helping scientists refine their models of the heliosphere, the protective bubble created by the sun's solar wind. Understanding the shape and behavior of this bubble is crucial for assessing the habitability of other star systems and the potential challenges of interstellar travel. Moreover, the Voyager's longevity, powered by their radioisotope thermoelectric generators, has demonstrated the feasibility of long-duration space missions, inspiring future explorations beyond our solar system. As the Voyagers continue their silent journey, they carry with them the Golden Records time capsules containing sounds, images, and messages from Earth, intended for any intelligent life that might one day find them. While the likelihood of such an encounter is remote, the Voyagers serve as a testament to humanity's curiosity and ambition to explore the unknown. Their mission reminds us that even as we grapple with the mysteries of the universe, we are also leaving our mark on the cosmos, one probe at a time. Now turning to the conclusion of our journey through 50 space mysteries, let's take a moment to reflect on the incredible questions that continue to captivate scientists and dreamers alike. From the enigmatic nature of dark matter and dark energy to the tantalizing possibility of extraterrestrial life, these mysteries remind us just how much we have yet to discover about the universe. Each mystery we've explored, whether it's the strange behavior of black holes, the origins of the Big Bang, or the unexplained signals from deep space, represents a frontier of knowledge waiting to be unlocked. What makes these mysteries so exciting is the potential for breakthroughs within our lifetime. Advances in technology, from powerful telescopes to cutting-edge particle detectors, are bringing us closer than ever to solving some of these cosmic puzzles. The Voyager probes, for example, have already pushed the boundaries of our understanding, and missions like the James Webb Space Telescope promise to reveal even more about the universe's deepest secrets. The pace of discovery is accelerating, and with it, the hope that we might one day answer questions that have puzzled humanity for centuries. But beyond the science, these mysteries inspire something even more profound, a sense of wonder and curiosity. They remind us that the universe is vast, complex, and full of surprises, and that there is always more to learn. Whether you're a seasoned space enthusiast or someone just beginning to explore the cosmos, these questions invite us all to look up at the stars and dream about what might be out there. So, as we wrap up this exploration of 50 space mysteries, I encourage you to stay curious. Follow the latest discoveries, ask questions, and share your thoughts in the comments below. What mystery fascinates you the most? Which one do you think we'll solve next? Let's keep the conversation going and continue to marvel at the wonders of the universe together. Don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update on the latest space discoveries. Thank you for joining me on this journey, and remember, the cosmos is waiting for us to uncover its secrets.